Hello everyone, welcome to our this video on computer science CBSE syllabus where we are going to cover two very important aspect of searching. So we'll introduce if you want to search an item, say for example you have created it in a file and you have seen and it is tested in your exam also that when you have to search for some aspect of that data, you have to read through the whole data set, right? And then you can make a decision whether that particular data that you are looking for is present or not. So that is the simplest form of searching where which is applicable when your data is unordered. But many a time you might be having scenarios where you have to repeatedly search and you like those search to be very fast. A lot of our use cases that you might be seeing in your day-to-day activity, particularly in online, when you are searching for some product or when you are uh, going through uh, you know any kind of website where website itself is trying to narrow down the set of recommendation for you. At many of those places there is a good interplay for some faster searching schemes. The one that we will focus is when your use case requires repetitive search, then you can sort your data, and on those sorted data you can do faster search. If sorting is very expensive, uh, in that case there is a some another set of technique which could fall somewhere between linear search and binary search, uh, where you so if you see, in case of linear search, you don't need any extra storage, right? You just have a temporary variable, and using that, you keep checking against all your data set. In case of your binary search, you have to actually sort your data set. So there is certain amount of overhead involved. Hashing is a technique where you can actually search faster than both linear as well as binary search given certain condition, but you need some additional temporary storage uh, so that you can actually store indices and try and reach to appropriate index with just couple of indirection in worst case and directly in the best case. So with this in mind, in this video we'll be actually covering and expanding on all three, and our major focus will be binary search. We'll have another follow-up video, a very short video, where we will cover some of your exam style questions, where you'll be given a data set of say array of integers or strings, and then you might be asked to find apply a linear search or a binary search, and then actually return that how many comparisons you have to do or where the index are. So that will at least cover in a follow-up video, uh, a short video. We'll try and wrap that in within 15 minutes sort of. So let us get started. A formal definition of searching: so this is the process of locating a specific element uh, called the key within a collection of elements. It determines if the key exists in the collection, and if so, provide the position. Now, linear search it checks each element of the list sequentially to find the key. It's very simple to implement, as you might see on this linear search algorithm box, right? So you provide the list or the where you want to search and the key, and simply you iterate over that list from begin till end and have a simple comparison, with current element and your key. If there is a match, you return the index, otherwise you return -1. So this is best suited for a small or unsorted list. Remember, there is advantage in doing linear search. If you have to do very infrequent search and your data set is unsorted, but this is going to be very inefficient for big data. Just as an illustration, so if you have this list 42 -2 32 and so forth as your list, and if you want to search for 8, what will happen? In this linear search loop, you'll start comparing from beginning. So 8 compared to 42, no match, move to next. 8 compared to -2, and then you keep increasing the index, right? Since in this particular case you are doing from left to right, your ith index itself will be right index. So in that case, we don't need to have an extra variable. And then similarly 32 and 8. Once you are comparing the 8, by this point in time, you are at third in fourth index and third in numeric. So you return 3 and you are done. So one of your question could simply be that given a list, search for an element and return the index. Of course, there could be multiple occupation of the key might exist, and implementation can take care of that as well. So best case doesn't make sense. I mean, it's just like you are lucky and the beginning itself your item is there. So best case is kind of not meaningful here. Your both average and worst case is OL. Why OL? Because one complete loop and you have to kind of go through it. Binary search here will spend some good amount of time, and this is also a topic which is tested more often, and many a time you are having 3 to 5 marks question. So in a definition perspective, so what you are doing in linear search, you assume that your list is unordered, and then from left to right you keep comparing. So you have to do on an average ON comparison, which could be prohibitive for big data set, and that's where once you sort it out, binary search can help you find those elements faster. So what it does is, rather than starting your search from beginning of the array, it actually finds the middle element. And why it finds the middle element? Because assumption is data is sorted, right? Now here is the deal, right? If your mid element is equal to the key that you are looking for, right, then you have got success, and you can return from there, right? If if in case you are not unable to find it at mid, then one of the two could happen, right? Either your key is less than your midpoint data. So it means that if your key is less, then every element beyond mid will be anyway not found. So then you actually narrow your search from begin of the array till mid -1, because mid element is not a match, right? So then depending on if your key is less than the mid element, you start searching from begin till mid -1. Otherwise, you know that if your key is present, it will be there from mid +1 till end. So that's how every comparison reduce and make redundant one half of your array, right? So that's why it is actually very significant, right? And so what happens again? Now you are say either having left half or you are having the right half, and then you repeat the process again. Find the mid element. If there is a match, you can return. If there is no match, then you check, compare with the key. If key is less, then actually you search on the left part, which will again be from the beginning of the array for that sublist till mid -1. Otherwise, you keep doing, on the right hand side from mid plus 1 till end of that array, this sub array now that we are talking about, right? And eventually it might be the case that you have reached to the uh, condition where your low is not less than high. It means actually you have crossed the mid position, so that will be one exit criteria. Otherwise it will keep comparing with mid, and if your loop breaks, nothing is found, it return -1, right? So if you take, we'll take actually in the next slide, we'll take an example and help you walk through it, right? But let us actually spend some time about understanding this binary search and little familiarity with code as well, because this is one piece of code that you might have to end up writing as part of your answer. As well as binary search is a very, very popular and one of the most used method for efficiently searching on sorted data set. So going forward, whatever path you choose, in your interviews and other things of variation, several variation of binary search will be tested, which will be part of your life journey. There are so many variation of binary search which can make this problem very, very interesting. So just to touch on the key characteristics, we need here that's this list is sorted, and this is efficient when data set is used. Otherwise, simply do linear search, right? Now look at the code. So we are starting with define keyword, and then we go for binary search, where we provide the list and the key that you need to search for. Then it is simply initializing both two variables, low and high, both to 0, and then low to 0 and high to the end of the array, which is length of this -1. And then it is setting up a simple loop, where it is saying while low is less than equal to high, right? In that case, every time it is finding mid by integer operation. You can see the double operator out there, right? So low plus height, and double operand 2. So it will only give you, because eventually you need numeric indices, right? And then it simply check, right? Does a comparison operator if list midpoint is equal to the key or not. If it is, then it runs the mids. Otherwise, it simply tests, whether the key is greater or higher. And if it is, key is greater than the mid, it sets your, your low. If your key is greater than mid, yeah, so it sets your low to, mid +1. Otherwise, it sets the high part of it, right? So one of the low or high is modified depending on this condition, and the loop continues until it finds a success. Now, very interesting thing, so far on your BIGO notation, you might have been taught that if there is a loop, it is ON. But you can actually do sort of simple arithmetic and sum this series based on some of your advanced based on regular math related things, where if every time your data set gets divided into half, then summation of those will go for log of n, not O of n, right? So very, very important, average and worst case complexity for binary search is going to be log of n, right? So with this, we'll take an example and say we have taken the same list, right? 5, 8, 13, 17, 32, 42, 44, and we want to find it for key is equal to 42, right? So your initial array, your mid element, so find the mid. What will be your mid? Low is 0, and then high is length of the array -1, which is 6. So 0 plus 6 by 2, what it will be? 3, right? So 0, 1, 2, 3, which is 17, right? So your mid element is 17, your key is 42. You compare mid element with key, right? Your key is higher. It means you move forward from mid +1 till end of the array. So in first step, you determine that your target sub array is right part of the sub array. So what is there? Beyond 17, it is 32, 42, 44, right? And here, if you see in this particular sub array, your now you are having 0, 1, 2, and if you look at low, mid, and high, it is going to be what 1, and that is 42. So now if you compare your mid element with key, it is a match, and so you return that yes, key is found here, right? Okay, very interesting. Now, so don't worry. What we will do, we will do couple of hands-on exercises in the next video. But let's quickly introduce hashing, right? So linear search, what is the key characteristics? Good for unordered, a smaller data set, but it needs ON comparison, right? To answer whether data is present or not, and at which index it is present. Binary search, on the other hand, needs to post process if your data is not already sorted, right? So sorting, as again, is so far the algos that you have seen, insert selection, insertion, and actually the bubble one, your average to worst case complexity ON square. But the other two that we introduced, merge sort and quick sort, they have log n complexity. So instead you have n log n complexity, right? So n log n is still actually the runtime complexity that you have. That is an overhead. So that's a question that given your use case, can you sort it out and then actually work on that one. Now many a time what happens is those sorting could be prohibitive, right? And still you want even faster search than binary. That's where actually comes hashing. Of course, there is no free lunch, and if you see the way hash is designed, it requires some additional storage, right? And the best case storage could be as many elements if you are having. If you create a duplicate, array as big as that, then every element, right, can be found in that hash. How? So say there are actually 10 elements in your array. Now if you actually declare another duplicate array of the same length, and you simply give so whatever data that you are having, right? Yeah, so that is another complexity, right? It's a range of data basically. That's the problem. Otherwise everybody would have been using hash, right? So just assume that say your data set is between 1 and 100, right? For simplicity, if your data set is between 1 and 100, then you can declare an hash of size 100 and keep storing. So say if you are actually working on a array of 10 items, right? So items are 30, 40, 50, 60, 70, whatever, right? So they are written on the same index. And so whenever you are searching for 30, you check that whether there is a data present on 30th or not, right? So in one check you can return. But what happens is your data are unbounded. So you work on a small, a small size hashes, and there actually you run into another very well-known problem. And this is the area where you should make yourself comfortable. There is a term called collision. So basically, what you do is, since you are not going to have a storage as equal to or of the same length as your your range of elements could be, so then you need to map them, right? Say for example, you can have any positive number, right? And you have actually decided that a hash of size 100 is good enough for you. Then any number that is coming, a very simple redirection could be take modulo say length of the hash, right? So as long as individually items are mapping one item to a slot, your storage could be limited to 100 and you can still answer in one go. But many a time that couldn't be the case. Say for example, right, you are saying modulo n and n is 100, right? Now if a number is 9, say 7, right? Now 7 modulo 100, what you will get? 7. So it means that 7 needs to be written in the index 7. Now say you get another element 107, and if you apply modulo 100, right, then what you get? Again you get to the 7th index. Now both 707, 207, 307, 1007, all of that will keep matching to the same index. Now the question is if there is a data, because what was your assumption? You know, if you take a hash, right? Let's again get back to the previous scenario. So say your range is only up to 100, right? And you declared a hash of size 100. So to find whether a data set is present or not, you can simply declare your hash as having no value, means there could be a Boolean indicator saying that that index is not set. Now when a query comes, you actually look at that index and you return that no data is present. But when a data set is inserted, you set that flag to true. It means that now there is a data set. So since there is no collision, presence or absence can be answered in just one comparison, right? But when there is a collision, so whether it was 7 that actually set that up, or 107 that set it up, or 1007 that set it up, right? That actually becomes a challenge. And how you are determining this, because you are assuming that at the max there could be only 100, 100 data set, right? There are several practical examples to support this particular constant. So now in this case, when 7, 107, 1007, 10,007, all of that match to one index, right? 7, with any of these, that particular record could have been set true. So then nobody could be sure that whether it is because of 7 or 107. So that's why there is a this problem where more than one data point can map to the same index is called collision, and there are actually collision redressal mechanism. Again, keep in mind what is the hash. Hash is a trade-off. If you look at linear search on one side and binary search on the other side, hash is something that is actually getting a faster search, right, with extra overhead of storage, right? And since you can't have infinite or the range of elements storage, you are going to work on some manageable depending on what your data says. In that case, many data points can match to the same index, so that leads to the collision point, and so you need a collision redressal mechanism. Now in the worst case, what might happen is, say your 100 data point that comes is 707, say 1007, 10,007, 1 lakh 7, 10 lakh 7, 1 crore 7, right? Say, worst case, all hundreds are like this. Then what happens is, the collision redressal mechanism says that you can have a linked list attached to that particular row. But remember, now you had a element of size 100. Your list itself could be of as long. So in that case, again, hash can, if your hashing strategy is not efficient, then hash can quickly deteriorate to a linear search mechanism with extra overhead, because every time, remember, in case of linear search, it's a very simple thing, right? Simply start from beginning, keep comparing till you find your element or reach towards the end, right? Here in case of hash, every time when you do comparison, you have to hash it out, hash course it, because there is a modulo operator plus some smart conversion from input data to something that can be mapped to some numeric range. So given all of this, a good hashing strategy with appropriate hash size could be a good trade-off for a faster access, and hash is used extremely effectively for large set of use cases. Wherever you heard terms like cache and everything, hash is in play. There are a lot of faster searching mechanism with limited additional overhead for hashing that is built around this. So in that we are kind of done with the theoretical part of it. Hash implementation will not be tested in your exam, and if you are interested, you can search on Google. You can actually drop a note in channel. You can have a video around hashing because practically it is one of those very important data set. So with this, we have introduced all three: linear search, binary search, and hashing. Let us so this code is actually not you will hardly be tested on in the coding part. You just need to know what collision is, and you might see a hash function here, right? It is simply doing key modulo table size, right? If you can see my mouse movement here, so this is the hash function, and if questions, if any, will actually be around that, right? Okay. Now let's quickly talk about time complexity. Since we are not talking about memory, so that is another term called memory complexity, right? So time complexity tells only half of the story, right? But anyway, here if you say linear search, best case is sort of useless. Let's look at average and worst case. So this is ON. Binary search, log n in both cases. Hash based searching, worst case could be ON, as we just talked about, and best case could be still average, could still be O1. Now let us take some examples as tested in your exam. So you might be given a list like this, right? As you see, search the key 8, right? In the list, and you might have to return which index it is. And if you see in this particular case, you can simply do a linear search, go from left to right, and 8 will be found in which iteration of it, 1 2 3 4th iteration, and it will be present on 3rd index, right? So that's what that is being asked here. The question that will be asked will not be programmatic. You have to just kind of apply linear search and answer. But binary search related problem you might be asked to code. So apply binary search to find a key in a list of certain integers, right? So say you are having 3 5 7 till 30, and you are actually randomly given a key to find. You can apply binary search. You saw the what is the binary search, right? It will actually we saw one implementation of binary search in our code here, and you can actually look at it carefully, right? You can use the same here, where you are simply initializing your low and high to begin and end of the list, and then you iterate from as long as low is less than equal to high, where you are finding the mid element, and if your mid element is found, you return success. If mid element is less, then you search from mid plus 1 till end of the array. Otherwise, you search from mid minus 1 till begin of the array. Okay. Okay. So comparing searching algorithm, what will happen? Say for example, if you are having this list, right, 50, 31, whatever, if you have to search one, right? So one is present. I think one is not present. So you have to do almost n comparison, right? 5 is again not present. So a lot of comparison. 55 is present. Yeah, almost the last one, right? And 99 not present, right? 99 present almost as the last one. So your linear search will actually give almost one comparison in practice. And then if you search and now apply binary one. So if you apply binary search, what will happen with this list? Say if you are searching for 9, right? How many elements are there? You go to the middle one, and yeah, so we'll actually see a coding of it. We also saw an example. Yeah. So hope you understood at least certain aspect of the 3 search that we talked about linear. It's the simplest one with worst case or best case complexity being ON. Binary search is having log n on an average, but it needs you to have ordered data set. It means there is a overhead of sorting if your data is not already sorted. And then hashing, which doesn't require your data to be ordered, but it's have extra overhead of temporary storage to hold that hash structure, and it needs a very good hashing mechanism. Otherwise, it will get into some condition that we call collision, and collision can deteriorate it to be a linear search with extra overhead. So with that, we'll stop here for our searching introduction. We'll again actually have we'll meet in the see you in the next video where we'll be actually taking your exam question around variation of binary search, and we'll be coding live. So see you guys there. Hope hope this actually help you revise your content in some way. Do like and subscribe my channel, and comment if any specific question that you might have. See you in our next video.